Okay, you notice up here on the top left-hand corner, you see that life is good, and notice that is grammatically not correct. Now, what is wrong with that? Life is gooder. All right. Number one, sodium hydroxide is soluble and aluminum hydroxide is not. Explain why. All right, the first thing you want to do is explain how they're similar, and then you want to explain how they're different. They're similar because they're both ionic compounds. Okay, so definitely they're both ionic compounds. Now, they're different because one of them, sodium, has a +1 and aluminum has a +3. So that obviously is the reason why aluminum hydroxide is not soluble. So your explanation would say that they are both ionic compounds. Hydroxides are both the same. However, the lattice energy in aluminum hydroxide is greater because of the +1. I mean +3. You could say that the +3 -1 attractive force is stronger than the -1 +1, but in essence, the reason is because aluminum is +3. Okay, let's look at number 2. Okay, magnesium sulfate is soluble, but barium sulfate is not. Okay, once again, how are they similar? They're both sulfates. They're both ionic compounds. They're both +2, -2s. So why is magnesium sulfate soluble and barium sulfate not? The reason is because with a large anion, the energy of hydration is greater with the small cation. Remember, cation is the positive charge, so this guy here is the cation, this guy here is an anion. And when you're dissolving, if all things are the same, the +2 and the -2, there's two parts of the game. One is the energy of hydration, which is the energy, the attractive force that the water has pulling on the ion, and then the other one is the lattice energy, which is basically the ions inside the crystal saying, that's not going to happen. So, if you have a large anion, then what happens is going down the periodic table, the difference in the lattice energy does not increase enough to actually make a difference. So with a large anion, the water molecule is more attracted to the smaller cation. So this means that the water molecule can pull harder on magnesium. Now the reason it's more attracted to the smaller cation is that +2 charge is concentrated in a very small point with magnesium, whereas with barium, it's a larger area. Okay, let's go down to the next one. The next one is the hydroxide question. Barium hydroxide is soluble, but magnesium hydroxide is not. First of all, what is similar is you've got +2s and you've got -1s. They're both ionic. Okay, so that part is the same. So the solubility would have to be either the energy of hydration, the water molecule pulling it apart, or the lattice energy holding it together or being very weak. In this case, you have a very small anion. And when you have a small anion, what happens to the lattice energy as you go down the periodic table is more dramatic. If those lines represent the difference between the nuclei between the cation and the anion, it's a much bigger difference. So, as you go down the periodic table, the lattice energy decreases because the distance between the ions the nuclei of the ions increases. And lattice energy will decrease with increased radius. In other words, the bond gets weaker as you go down. So the answer to the question, barium hydroxide is soluble, but magnesium hydroxide is not. The answer to that question is the lattice energy between barium and the hydroxide is weaker because the distance between the nuclei is greater. Barium is much larger ion. Okay, so now let's get to the fun part with the calculations. The solution is prepared by adding 125 grams of sodium phosphate into 850 grams of water to determine the freezing point and boiling point. Well, the change in freezing point equals the constant for freezing times molality times the number of parts. Change in boiling point will equal the constant for boiling times the molality times the number of parts. Sodium phosphate, Na3PO4, will split into 4 parts. Each of the sodiums will be a part, and the phosphate will be a part. So the first thing we need to do is find the molality. So the molecular weight of sodium phosphate is 164. So I need to find the moles per kilogram. So I'm going to say 125 grams divided by 164. That's going to give me moles. So that's 125 divided by 164. That's 0.76 moles. And then per kilogram of solvent, I have 0.85 kilograms. So divide that by 0.85. That gives you 0.8967, or we can just call it 0.90. That's the molality. Okay, the freezing point constant for water is 1.86. You'll be given that. And the boiling point constant is 0.512. So the change into freezing point is 1.86 times 0.90 times 4 parts. So 1.86 times 0.9 times 4. The change in freezing point equals 6.7 degrees Celsius. So the new freezing point is going to be negative 6.7 degrees Celsius. When you're looking at significant figures for this, 125 grams is 3 significant figures, but 850 is only 2, so your answer is going to be 2 significant figures. Okay, the change in boiling point is going to be 0.512 times 0.9 times 4. 0.512 times. Okay, so that equals 1.8 degrees Celsius. So the new boiling point is 101.8 degrees Celsius. That's one answer. That's another answer. Okay, number 5. Well, we know this one, yeah? Okay, what's the vapor pressure of a solution that is 25% sodium chloride by mass? The density is really not needed, but it's given. And the vapor pressure of the pure solvent is 23.9 millimeters of mercury. Okay, if you have a solution, then the vapor pressure is going to be lower than that of the pure solvent. So here, the vapor pressure of the pure solvent is 23.9, so I know the answer is going to be less than that. All right, 25% sodium chloride by mass means I have 25 grams of sodium chloride in 100 grams of solution. Vapor pressure changes by the mole fraction, by basically the percent of moles. So I'm going to need to change this to percent, or to moles. So this is 0.43 moles of sodium chloride. I divided it by 58. And then remember that the solution is actually 25 grams of sodium chloride plus 75 grams of water. So the solution is actually the salt and the water together. Well, we know that's already 0.43 moles. And so the 75 divided by 18 is 4.2 moles. So the mole fraction of this solution then, which would be X, funny looking S, X, is going to be 0.43 over 4.63. And you leave mole fraction as a fraction. So the answer is 0.093. That's a mole fraction. In other words, this solution is 9.3% sodium chloride by moles. So what's a new vapor pressure? Well, the change in vapor pressure equals the original one times the mole fraction. So the change in vapor pressure is 2.2. The new vapor pressure then would be 23.9 minus that, 21.7 millimeters of mercury. Okay, the other way of doing this is just to acknowledge the fact that if this solution is 9.3% by solute, then it is 90.7% solvent. And 90.7% of 23.7 is going to give you your answer. Okay, also, there's a little glitch on this one. This is sodium chloride, and sodium chloride actually breaks into two parts. So when you're actually calculating the moles, you would multiply that by 2 and make that 0.86. So this guy would actually be 0.86 also. And so that's going to alter your results just a little bit. And it makes the mole fraction 0.17, which lowers it 4 and gives you another answer of 19.8. But I didn't point that out at the beginning because almost always you're going to be given one part for the mole fraction, and that's how you do it. Anyway. Okay, number 6, this is fun. Okay, number 6 says, okay, let's change here. Really. Okay, so number 6 says, a compound containing carbon, hydrogen, and oxygen is burned. Okay, and this is what you get. And then it says, in another experiment, I'm going to get this other stuff, which is the freezing point information. Okay, the top part, the carbon something, hydrogen something, oxygen something, it's burned in oxygen to give you CO2 and water. This information is given to you so you can find the empirical formula. You have 1 gram sample of this, and you make 1.418 grams of CO2 and 0.871 grams of hydrogen. Okay, you need to acknowledge the fact that all of your carbon right here in the CO2 came from the carbon in your unknown compound. And if you find the percent of mass for here of CO2, then you can multiply that and get the carbon. So the percent of carbon in CO2 is going to be 12 over 44, which is 27.3%. So 27.3% of 1.418 grams is going to be the number of grams of carbon. So that's going to be 30 or 0.387 grams of carbon. Those grams came from this guy over here. So that guy right there is 0.387 grams. And we could set it up the empirical formula way here. It's 0.387 grams of carbon. I'm going to just divide it by 12 right now. And that gives me 0.03 moles. Okay, for the hydrogen, the percent of hydrogen in water, there's 2 grams of hydrogen over 18. That's 11% hydrogen. So 11% of 0.871 is your grams of hydrogen. So there's 0.096 grams of hydrogen. And that came from over here, 0.096 grams. So I'm going to put that down here, 0.096 grams, divide it by 1 to get it into moles. And right now I see that's 1 to 3. Okay, your oxygen I'm going to get by subtracting from 1, because the whole compound weighs 1. 0.387 grams of it is carbon. 0.096 grams of it is hydrogen. So that leaves 0.517 grams of oxygen. 0.517 grams. Divide it by 16 to change it into moles, and I get 0.0323 moles. You see that's a 1:3:1 proportion, but if you don't, you could set it up. Divide by the smallest one, or as we have learned, that handy dandy calculator that your mama paid a lot of money for would do this for you. And CH3O is the empirical formula. Okay, holy cow. The next part is where you want to find the actual molecular weight. So it tells you 0.1103 grams of the compound dissolved in 45 grams of water and had this freezing point. Okay, so let's do this up here. The change in the freezing point equals the constant times the molality times 1 part. 1 part because it's not ionic. The freezing point change is 0.0734 degrees because water freezes at 0, so the change had to be that. The constant's 1.86, and we're looking for the molality. 0.0734 divided by 1.86 today is 0.039, so the molality is 0.0395, which is moles per kilogram, and it's 0.045 kilograms of solvent, and that gives me 0.00178 moles. All right, molecular weight is grams per mole. So we had 0.1103 grams in 0.00178 moles, and that gives me 62 grams per mole. Okay, so what's the real question? The question is, what's the molecular formula? All right. The empirical formula is this. It weighs 31 grams when you add up 1 carbon, 3 hydrogens, and an oxygen. The molecular weight is twice the amount, so the real McCoy on any given Friday is C2H6O2, and that is another reason why life is good. One more. Number 7. An experiment was conducted. Well, that's nice. To determine the molecular weight of an unknown compound, in the experiment, 20.15 grams of lauric acid is added to the test tube. It melted. The freezing point temperature was measured here, 44.8. Next, 15 grams of the unknown was, well, doesn't this just seem like a lab? 15 grams of the or 1.5 grams of the unknown. And now, the solution freezes at 41.9. So, lauric acid is your solvent. You need to find the molecular weight of the unknown compound. So your molecular weight of the unknown compound is going to be grams per mole, and we have 1.503 grams. Okay. We have 0.02015 kilograms of the solvent. First, we need to find the change in freezing point. That would be 44.8, which was the normal freezing point, minus 41.9. So 44.8 minus 41.9 today is 3. Well, yep. Okay, 2.9 degrees Celsius. So the change in freezing point equals the constant times the molality times the number of parts. So 2.9 equals 3.9 degrees Celsius per m, that's the constant, times the molality times 1. Molality comes to 0.74, and that's going to be moles of your solute per kilograms of the solvent, and we have we use 20.15 grams, so that's 0.02015 kilograms, and 0.02, and that would be 0.014, or let's make it 0.015 moles. Okay, that comes up here. That 1.503 grams was actually also known as 0.015 moles, and I get 100 grams per mole. All right, I do believe that we're done. And that's it. Don't drink and drive. Don't do it. Bad. Just say no.